Chapter 1. Finding Andromeda. At first glance, it's a soft, cigar-shaped smear in the northern autumn sky, nestled in the constellation Andromeda. In reality, it's the nearest major spiral galaxy to ours, roughly 2.5 million light-years away across the dark. You can see it with the naked eye from a dark site. What you're seeing is the combined glow of 1 trillion suns suspended beyond our Milky Way's rim. Astronomers call it Messier 31, or M31. Measurements place its distance at approximately 765 kiloparsecs, approximately 2.5 million light-years, and its apparent disk spans well over a third on the sky, 6 full moons end to end. Chapter 2. A neighbor on a slow-motion collision course. Andromeda isn't just nearby, it's coming toward us. Its light is blue-shifted, indicating approach at roughly 110 kilometers per second. For years, simulations projected a merger with the Milky Way in approximately 4 to 5 billion years. Recent reanalyses with Hubble and Gaia data suggest the future is less certain, anywhere from a direct merger on multi-gigayear timescales to a long, grazing dance, about a 50-50 chance of a true collision within the next 10 billion years. Either way, stars are so far apart that very few would hit. Instead, the two galaxies' halos blend, their disks distort, and a new elliptical or lenticular remnant eventually forms. Chapter 3. Anatomy of a giant, bulge, disk, and the 10 kiloparsec ring. Andromeda is a barred spiral with a bright central bulge, sprawling stellar disk, and striking rings of dust and star formation. Infrared maps from Spitzer and Herschel reveal a prominent ring approximately 10 to 11 kiloparsecs from the center, and additional inner/outer rings, where gas and dust are heated and new stars ignite. Much of the current star formation is concentrated there. Chapter 4. The Core Mystery. A double nucleus and a massive black hole. Peering into the heart of M31, Hubble found a quirky double nucleus, P1 and P2, evidence for an eccentric stellar disk orbiting a central supermassive black hole, M31 star. Mass estimates vary by method but typically land between approximately 5 times 10 to the 7th and approximately 2 times 10 to the 8th solar masses, significantly larger than the Milky Way's central black hole. The dual-peak light is best explained by stars bunching at apocenter in an off-center, eccentric disk around the black hole. Chapter 5. The giant halo you can't see. Around the luminous disk is a vast, hot, diffuse halo of gas, the circumgalactic medium, CGM, mapped with Hubble using backlit quasars. It spans approximately 1.3 million light-years in typical directions, and up to approximately 2 million in some, reaching halfway to the Milky Way. The inner halo is clumpy and shaped by supernova feedback. The outer halo is smoother and hotter. This reservoir is a major piece of the galaxy's ecosystem, trading metals and energy with the disk. Chapter 6. Ghosts of past meals, streams, satellites, and globulars. Andromeda's halo is crisscrossed by tidal streams, most famously the giant stellar stream, debris from a devoured companion within the last few billion years. M31 also shepherds dozens of dwarf satellites, M32, M110, and many ultra-faints. HST mapping places approximately 36 dwarfs in its immediate system, and it hosts approximately 460 to 500 globular clusters, including G1, Mayall-2. So massive it may be the stripped core of a small galaxy, and might even harbor an intermediate mass black hole. Chapter 7. What Andromeda might be hiding. A trillion-star city implies billions of planets, from hot, inner-orbit worlds to cold rogue planets adrift in the halo. X-ray surveys reveal populations of neutron star and black hole binaries, supersoft sources, and supernova remnants peppered through the disk and clusters. And while no technosignatures or megastructures have been confirmed in M31, astronomers are actively searching, from optical laser beacons to mid-IR excess that could betray Dyson-like waste heat. To date, the results are null or ambiguous, but the search is ongoing. Chapter 8. How far is too far? The hard math of getting there. Even at relativistic speeds, the gulf is staggering. At 0.2 c, a probe would need approximately 12.5 million years to reach Andromeda. 0.1 c takes approximately 25 million. 0.01 c about 250 million. And that ignores acceleration and braking. Energy is punishing too. Pushing a 1-ton craft to 0.2 c requires approximately 1.85 times 10 to the 18th joules of kinetic energy, about 515 terawatt-hours, or approximately 443 megatons TNT equivalent, before real-world inefficiencies. Intergalactic space is emptier than our ISM, but dust at relativistic speeds can erode and puncture. Shielding and clever profiles are mandatory. Chapter 9. Propulsion concepts on the table and their limits. Fusion megaprobes, e.g. the BIS Project Daedalus lineage, sketch out uncrewed interstellar shots at a few % of light speed, still far from extragalactic timelines. Nuclear pulse concepts, Project Orion, deliver huge thrust and specific impulse but face engineering, political, and environmental barriers. Beamed sail concepts like Breakthrough Starshot aim for approximately 0.2, but only for gram to kilogram probes. Scaling to ton-class vehicles is orders of magnitude harder. Warp drives and traversable wormholes remain speculative with no experimentally validated pathway today. For Andromeda, all current roadmaps point to robotic probes, not people, and to timescales far beyond civilizations, unless physics or engineering makes a step change we don't yet have. Chapter 10. The sensible first steps. Touch. Andromeda. From here we can probe Andromeda now by mapping individual stars, H2 regions, clusters, dust rings, and halo gas at exquisite resolution. The That Hubble mosaic alone charted over 100 million stars. Hubble/COS observations dissect its halo. Ground surveys trace its stellar streams. Radio arrays map cold gas. Even SETI teams target M31 for laser or radio beacons simply because its star count offers a trillion opportunities. The frontier is open today, without leaving home. Chapter 11. If when we arrive, what we'd likely find. Expect a familiar but not identical spiral city, older bulge populations, active but modest star formation. Typical global estimates range from approximately 0.25 to approximately 1 solar mass per year, with strong activity in the 10 kiloparsec ring, metal-rich inner regions and metal-poorer outskirts, and a halo stitched with streams and accreted clusters. The nucleus may flare episodically as gas trickles onto the SMBH. Planet catalogs would explode, from hot Jupiters skimming suns to rocky worlds in gentle, older orbits, to frozen giants far out. Chapter 12. The Long View. Our Shared Future. Whether the merger is nearly certain, or only coin flip likely, Milkomeda, A blended future galaxy remains a leading scenario over multi-billion-year horizons. The night sky then would bloom with tidal arcs as Andromeda stretches across it. Long before that, we'll keep sharpening maps, combing for signals, and learning how galaxies breathe. The road to Andromeda may be unimaginably long for travelers, but scientifically, we're already on it.